Okay, thank you very much for the introduction. And I would like to thank actually the organizers very much for inviting me here to give this talk, and for these 2 weeks I've spent here in Bonn, which is a lovely city, and I enjoyed very much to be around. So let me tell you a little bit of this work I'm going to present. Is concerning with images. It has a lot of optimization going on, and it has some flavor mainly at the end of what the difference is between local and non-local models in imaging. And I will try to show you how this can have an effect, and how what we are aiming to in the context of image processing, and mainly in the context of bilevel learning in this setting. So first, my co-authors, I've been working for a while with Carola from the University of Cambridge in this topic, and Cao Van Chung, who is a co-author of the main part of this work, was a postdoc in our group, and now he moved back to Vietnam. And the outline of the talk is the following one. First of all, since this is not precisely an image processing community, I wanted to introduce some facts about the generalities of the variational models and how the image processing works in that setting. Then I will explain you in detail, with more technicalities also, what the optimal TV denoising is about. The spatially dependent case, which I will go next. And finally, in the fourth part of the talk, I will explain you a little bit of an ongoing work, which is joint work with Marta Delia and Juan Pablo Bortagaray, which is about the non-local models that we are interested in, actually. So first of all, the main variational setting for the processing of an image is the following one. So in general, what you get is actually an image which is corrupted by some typical or some noise. You may know in advance which type of noise you have, or you may not. But you observe something which is corrupted by this type of noise, and may be affected by some sort of a forward operator that you have affecting the image. So you observe the noisy image, and what you want is to reconstruct the image out of it, mainly by inverting, if it's possible, of course, if it would be possible to invert this operator and get some sort of a reconstruction out of it. Now, in general, what you have is that this operator it has an unbounded inverse, and even if you have an identity there, it is not easy to recover the image which is the original one that you want to. So usually what you do in this setting is to regularize in some way to add some information you have a priori about the image you want to recover, and in that sense recover the best possible image you can. So in general, what you have is actually a functional you want to minimize, which is composed by these two elements. First of all, you have the noise model, which is given here, which comes from some sort of I'm sorry, this is the distance function given here, some sort of understanding what's about what is behind the image acquisition. So you may have some physics there, and you may know which kind of noise model you are going to have in the image, or some clue about it. And a part of that, you have this important term here, which is called the prior, and it gives you some information, some a priori information that you want on the image. For instance, if you want to recover an image which is in the Sokolov space H1, then you may use for the regularizer an H1 norm. And that has the effect that the image you recover is in H1, right? So you may include H1 or other spaces, but mainly this is the information you have a priori about the image that you want to recover. Now you have an important element here, which is the weight, which is weighting one against each other. And so you have to balance between how much you want to regularize and how much you want to be confident with the noise model you had at the beginning. I'm going to this in detail in a while. So the results, of course, heavily depends on the correct modeling, and that implies both things, the image modeling that you have and also the type of regularizer that you are going to use. And in both cases, and that's kind of the message of this part, you can also recover some information out of experiments you may have in advance in a previous stage. So what difference does it make to have the different type of regularizers and the different type of data models? So this is the basic total variation denoising methodology. And what you have in the total variation denoising setting is an image you want to recover. This is the noisy image, and you want an image to a reconstructed image which is as close as possible to the noisy image in this Gaussian setting there. And of course, if you do a minimization of this part, it's quite easy to obtain the same image you had at the beginning, so you are not doing really anything out of it. What you add is some variational, some total variation term on it, so that you can recover an image which preserves. This is a very basic example with a noisy signal. And what you want is to recover some function which is the black line here. And the black line here does get rid of the oscillations in most of the signal part, but it preserves the jumps, right? So the effect of the total variation is exactly that one. So it preserves big jumps on the signal, but it gets, it puts away the whole spurious oscillations out of it. And of course you have to balance the one against each other, but the main thing you want to preserve is these important jumps out of the signal, right? So if you put some weight, you have to weight the noise model against the regularizer, and you have to choose this lambda in a wise way. What does it mean? Well, here you have an increasing regularization value, and if you do not put a lot of weight, then you mainly recover the same noisy image that you had at the beginning. This is the noisy image you want to process. This is the one you get if you under-regularize in some way. Then you regularize a little bit more, you get this image out of it, and then further you get this one here. Now the noisy image, which is in the last part, is of course something you don't want to get, because you get rid of the whole details of the image. What you want is to read or to be able to identify some objects or some spots in the image, and here you over-regularize the image, and here you under-regularize. So what you want to recover is something which is in between, and that means you have to tune the parameter lambda quite a bit to get the best reconstruction, or the best possible reconstruction you can get. Now this is the effect of the regularizer in, in the images. So this is the original cameraman image, this is the noisy one, and here you have a regularization with a Sobolev space term. And as you can observe in that setting, you get a little bit of diffusion all over the image, and that's not really what you want to reconstruct. If you want a remedy, an easy remedy to this one, what you use is the total variation, as I mentioned before, and you preserve the edges of the image. At least that's the effect, or the main effect, that the total variation has on the images. And this has been around for a while already. And in the non-local means, what you want is actually, and that's the main interest of our work right now, you may not want only to see the whole edges locally, but you may want to learn also from the neighborhoods with similar intensities. Let's say you have gray and white or a grayscale intensity pattern. You want to learn from that intensity pattern to be able to reconstruct the image with the non-local information. So this kind of non-local means has also been around in the last years, and this is a simplified version, a modified and simplified version with some kernel given here. And you can observe in this image, with this is the noisy one, this is the image recovered with the total variation, and this is the image recovered with the non-local means method. And what you can observe is that in the total variation you can reconstruct the spots in the zebra when they are really far apart from each other, and that's something that you expect from the total variation actually. But for instance, in this gray part, you have this sort of patches, this sort of artifacts, which are quite natural to be obtained by total variation, but it's something you don't want to get. And a part of that, the reconstruction of this pattern here, this textured kind of pattern, which is given with these small spots, is not really very nice in the total variation sense, while in the non-local, with the non-local filter, with the non-local method you can recover something which is better with these type of fine structures that you're interested in that setting. So a part of the regularizer, there is an effect that you have on the data term, and you have the different noise models that I was talking about before. So this is the typical Gaussian, is the easier one that we use all the time. This is the Gaussian noise model. You have the Poisson noise model. You have the impulse. For instance, these are the three typical kind of noise models you use, and you can imagine that what happens if you apply the Gaussian noise model to this image. You are not going to recover this one, for instance. So you have to really know in advance a little bit about the acquisition of the machine, or you may want to apply some setting to learn that automatically. Now, the choice of the parameter actually, or the choice of the weights or the whole parameters of the denoising is also a topic which has been around for a while. And mainly there are works based on, for instance, the type of noise level that you have in the image. Let's say you have an image where you know in advance that it has some sort of noise and it has some variance, some expectations and so on. You may apply this information to get the parameter in a better way. But in most of the cases, you don't know that in advance, right? You are not really very sure about the noise model that you have in your image. So there have been works concerning the choice of the noise model, either with that known statistics of the noise, either adapting the noise model, using different type of regularizers, some Bayesian community which has been also working on this for a while. And what we were interested in actually was some more machine learning approaches towards this choice of the parameters involved in this image denoising task. So let me tell you about that a little bit more. So in some applications, what you have is actually some sort of training set of images you can learn from. You have images where you can say one image is the true image while the other one is the noisy image. And that happens, for instance, in medical applications where you can have some sort of machine and you have the exposure time of the machine in some sort of phantom, and you expose that phantom 2 days in the machine, then you get a pretty good image out of what is going on behind. That's something you can consider as a true image that you have. Of course, if you have a patient, you don't want to put the patient in the machine for two days. You want the result as soon as possible, right? And in that case, what you can do is learn from that ground truth image, which is this high definition imaging. And you can also use the imperfect data, which is the noisy data, to obtain some sort of clue about the parameters of the optimal parameters you have in mind. So what you do typically in this setting is you consider the minimization with respect to the whole parameters that you are using in your denoising model and try to get as close as possible to the ground truth image which is given here. And this image that you have is the reconstructed image out of your variational model. So you put or you set the lambda in an optimal way in such a manner that this one is as close as possible to the ground truth image that you have from the beginning on. So you have a training set and you want to learn from that one by comparing with the image you can obtain from the reconstruction model you are using, which is a variational one in this case. So this is an example of what it can be with the training set. These are the images which are high resolution MRI scans, and these ones are the low resolution MRI scans. So this is an exposure time which is very short, while the other is a longer one. And you can consider this as the training set you can learn from. Now, in our case, the choice of optimization, and specifically of bilevel optimization or optimal control in the context of image processing and the learning in image processing has been around since 2007 mainly, I would say. And these authors work on some models called the Markov random fields. Then there are a couple of works concerning optimal control approaches, and we started working with this in 2013, and since then there have been other authors also considering this type of setting to obtain some parameters which are optimal in some sort of way. Now, what we wanted from the beginning on was to consider the whole problem in function space and to learn to be able to solve, to pose and study the optimization problem in function space. And so we consider the problem, the non-smooth optimization problem in this setting and try to stay as close as possible to the physical model. This has two implications. First, we try to preserve the properties of the infinite dimensional image, which means basically the structures which are hidden behind, like the edges, for instance. But secondly, what we want is also to derive Lagrange multipliers to obtain some mesh-independent optimization method for the image. What we don't want is some optimization routine that takes some iterations for a low-dimensional image and much more for a higher dimensional one, so we wanted a robust methodology to deal with that. And a part of that, an implication which comes out of this optimal setting is in many cases where you don't know actually which type of noise model the image has. It's not really Gaussian, it's not really Poisson. You don't really know exactly which kind of model you have. You try also to recover some model out of your optimization problem that we have. So this has, of course, some implications concerning the treatment of the problem. And this is the TV denoising problem again, and this time is a little bit more generalized. What we used here is more weights combining the different noise models that you may have. If you combine Gaussian, Poisson, impulse, you combine different type of models, you may want to solve the problem and tune the parameters so that you recover the best noise model that is according to your image in that setting. Now, as I mentioned before, there are a couple of noise models around, and what we want actually is to weight the different type of models against each other to obtain the best possible combination for recovering the image. Now again, in our setting, we were trying to deal with this training set and these training images and try to approach as much as possible what we consider the ground truth. You may want to use the L2 norm, but you may also use different type of cost functionals there to compare the performance of the image. And our lower level problem, our constraint problem, is concerned with this total variation denoising problem. So we want to choose these coefficients lambda I so that this is minimized subject to this constraint. Now in principle, when you look at the function space setting for this type of problem, then what you can obtain here is at some bounded variation space where you can recover your image. Now this bounded variation space is not really something you want to deal with when you are trying to optimize and to find some optimality conditions for that. So what we did in this context was to replace this optimality, this optimal problem, this variational problem in the lower level part with some elliptic regularization we add here on this term. Now this parameter may be as small as you want, but it has to be there to recover some regularity of the solution, right? And if you consider these optimization problems, so you have an optimization problem on top of the other optimization problem, it's not something you can deal easily with. So what you usually do is actually to replace this type of problem with an optimality condition which is necessary and sufficient in this setting, in the sense that you are considering only convex terms in the functional. And if you replace this with the necessary and sufficient optimality condition, what you get is an optimization problem subject to a variational inequality or a variational inclusion in this context. Now typically what you do in optimization or optimal control is you try to prove actually what the properties of the solution operator are. So you want to recover some sort of differentiability maybe of the solution operator so that you can use some derivative-based methods. And in this context it's quite difficult to get a nice differentiability result. So what we did in the beginning was taking a look at the literature which was around and see what can be obtained if there are some sort of Lagrange multipliers that can be obtained in this setting. And these Lagrange multipliers are the key tool for designing optimization routines, right? So we took a look at the literature, and in these contributions, there was some existence of Lagrange multipliers, but the Lagrange multipliers were not properly characterized. So there was really something missing there to being able to exploit that information, that derivative-based information. So when we considered this type of problem, we were also thinking about making something more specifically to the type of regularizer that we had, or the type of term that we had. And so the total variation is not a general variational inequality for every convex kind of function, but it has a specific structure that you may exploit in some ways. So the first idea that you have usually in this setting is to regularize the problem. And if you regularize the variational inequality, what you obtain is actually a partial differential equation of quasi-linear type. And this partial differential equation, if you regularize, you may have different outcomes actually. And so the first thing we realize is it is important the way you regularize this term. So you may regularize this subgradient, which is given here, the subgradient of the absolute value. You may regularize with some C infinity function, or you may regularize with something that actually touch the bounds of -1 and +1 in different parts of the domain. And this has an effect on the optimality condition that you can obtain afterwards. So it was important to realize that actually these type of functions work analytically, while these ones are not useful for getting a fine optimality condition at the end. So what we could prove in this setting actually, and that was kind of the main part of the first work we had in this context. First of all, what you want to prove is the existence of an optimal solution, existence of optimal parameters, the optimal image. But then you want to get, I mean, if you regularize, if you use an elliptic regularization, then you are adding, if you use again a Hoover type regularization like the previous one, you want also to have convergence or some sort of convergence if your regularization parameters go to 0 or go to infinity, either way, and to justify and to have a consistent scheme, right? So what we could prove in this context was a part of the existence of the optimal solution. We could prove something which is of importance in the numerical part, and this is that the optimal parameters are actually greater than 0. It cannot be 0. We proved also some outer semi-continuity of the solution map, the differentiability of the solution operator, of the regularized solution operator, and some convergence of the, when gamma goes to infinity, to a sharp optimality system for the non-smooth problem, and also some gamma convergence of the denoising functional as ellipticity goes to 0. Now, this gives us a consistent scheme for the approximation of the problem, and this is how actually the optimality system looks like for the regularized problem. And for the ones that have been working on an optimal control for a while, this is just the state equation, which is the equivalent of the denoising type of problem. You have also an adjoint equation, which is given here, and you have something which we call the gradient equation, which characterizes actually the gradient of the cost functional. If you have the gradient, then you may want to use some optimization routines for dealing with that. Now, this is an analytical slide mainly, and it tells you that as the regularization parameter goes to infinity, then you can recover also something which is an optimality condition for the problem without the regularization. So you do an asymptotic analysis in the optimality system, and you recover some sort of optimality condition for the original problem. Now, this optimality condition for the people working on non-smooth optimization is equivalent to something which is called the C stationary point, in the sense of Clark is the C given here. Now, coming back to the previous slide, we had a characterization of the gradient, and this characterization of the gradient leads us to the development of some numerical methods for solving that, right? So for the numerical approach, what we used actually for solving the bilevel problem is some sort of quasi-Newton type method. And for each denoising problem, since we had already a regularization going on, we use a semi-smooth Newton method, a globalized one in that case. The evaluation of the gradient was performed using the adjoint information we had before. And since the optimal parameters are strictly greater than 0, we require really only a mild treatment of the constraints. So if there were not really positive constraints in the sense that you need to project each time, because we knew in advance that the parameter was greater than 0 and could not be equal to 0. And we use also some update of the DFGS matrix when the curvature condition was actually verified. Now these are a couple of examples of the problems that we solve. This is a combined noise model with Gaussian Poisson noise, and what we could recover is actually some lambda 1 and lambda 2, which are optimal for denoising this image. This is the original one, this is the noise image, this is the one that we recover. And if you are not satisfied with the outcome of that image, it's because what you are using is actually an L2 norm in this comparison you have above. We can improve that and use different cost functionals, but this is optimal concerning this L2 norm. So what you get out of this, more important than that, is that you have a combination of noises, lambda 1 and lambda 2, which leads you to a better reconstruction of the image you are interested in. So you may also use that for some impulse noise, in the sense that these are also, or this is also a non-smooth term involved there. This is the noisy image, this is the original image, and this is the one that you can reconstruct out of it. And in the case of impulse noise, it works quite well in that setting. So the partial conclusions of this part are, first, we can choose the parameters for variational regularizers. Actually, with some bilevel optimization problem in function space, we can deal with that. We can extract some information, prove some theorems concerning the operator. And these are involving existence, positivity, differentiability, and some other results concerning that. But the next thing that we asked ourselves at that point was if it is possible to extend that in some, we are solving the adjoint, we are solving a lot of problems which appear quite involved if you just want one parameter out of it, right? But the tools are already there, so the tools were already developed, and what we ask ourselves is if it's possible to use those tools in a different setting when we don't want to optimize only parameters, but we want to optimize functions by themselves. And that has some applications in what is called the spatially dependent noise. And in this case, these are two images where in this red part, you can see, or you can, well, I don't know if you can really see, but the noise is much higher in this part than in the rest of the image. So there are typical applications. Here is another example where you have different type of noises or noise intensities within one image, and you want to recover the best image out of it. And it doesn't really mean that you need a constant parameter for the weighting between the terms that you had in the variation of functional. So in this setting, the optimization problem looks like this. And it involves the lambda, but the weighting lambda that we had before is now a function of x. It's not a scalar anymore. And it takes care of the irregularities of the noise in the different parts of the image. And what you have to add, sadly, but you have to add some Tikhonov regularization term for the parameter in the space you want to look after the parameter. So we started looking at the parameter in the H1 space. And in a similar fashion as what we did before, you end up with an optimal control problem where you have this partial differential equation as constraint, but you have also some positivity constraint of the functional on the functional parameter you have now. Before it was a scalar, we could prove that that scalar was away from 0 actually, but now you have a function. And you have to consider this sort of constraint in the problem setting itself. So it is, or it constitutes a PDE constraint optimization problem with control constraints, and you have also controls on the coefficients of the PDEs itself. So what we could prove here is that there exists an optimal weight which solves the bilevel problem actually. We could prove also that the solution operator is Frechet differentiable, and you can also, I mean, this is for the regularized operator. And what you need actually is some extra regularity result, both for the Frechet differentiability and also for getting some Lagrange multiplier. And you get this regularity result out of obstacle type regularity problems for obtaining or for getting the differentiability result. Now the optimality system in this case is looking like this. So you have again the state equation, which is now using an additional variable, which is called Q. This is the adjoint equation, and what you have is now this PDE, this extra PDE, as the gradient equation of the problem, and you have a part of that some complementarity system. Now if you take a look at this, this is, you need really an efficient complementarity solver in this case. And so there's something I didn't tell you so far. If you use just one training pair, then you end up with a system which has 3 PDEs. But if you are using a lot of information, if you are considering really a training set of a lot of images, you have for each training pair one PDE, one adjoint equation, and you have all of them coupled to each other. So you may end up with a lot of PDEs you want to solve at the same time, right? So what we did in this setting is to consider the solution of this nonlinear complementarity system, and for that we used Schwartz overlapping domain decomposition method. So first of all, we split the image in different domains. Then we consider the transmission conditions between the domains in an optimized way, considering a Fourier coefficient analysis. And a part of that, we solved each complementarity problem with a semi-smooth Newton method in each of the subdomains, and then we consolidate everything together. Now, this is the original image that we wanted to reconstruct. This is a noisy one with a higher noise in this part of the image. And what you obtain is actually a regularizer. This is the result. And this is the regularizer you obtain with this intensity, which is even higher for the regularizer in this part of the image, which is something which is natural from the image you started with, right? So if you do a constant reconstruction, you use just a constant, you don't get such fine results in this part or the other, right? So you really need to consider this non-uniformity of the noise in that setting. This is a surface plot of the optimal weight, and as partial conclusions of this part, what we could actually was solve the spatially dependent problem, and this is important to get a sense of what the non-homogeneous noise is about. But you can also learn there how the noise model is. So if you have some parts of the image where are not really adjusted to the noise model, then you can learn and try to model the noise in a different way. And actually we could solve that numerically, and our method was good comparing to other state-of-the-art methods like the ICTV, which is around there. Now, the question now that we have since a couple of months is if it's possible to extend the methods to cope with non-local regularizers. And so, as I mentioned before, the local methods may fail in some important part of the images, right? So there are some situations when non-local can have a better behavior in reconstructing some thin structures of some texture in the images. And the goal is actually to preserve those details and those textures. And our goal is, in a very general setting, is to learn from a given training set of images which is the optimal non-local denoising functional we have to use for a given set of images. So in this context, what we can formulate is the minimization problem, the lower level minimization problem in this way.
So we have the minimization of a functional J, which is composed by this energy and the noise model we had before. This is just the Gaussian noise model for starting with. And this J here is the non-local energy norm of the image, which is given in standard way in this form. And this non-local norm is related to this diffusion operator, which is given here, which has this important element, which is the kernel gamma. Now you can write down the Euler-Lagrange equations for that lower level problem. And these Euler-Lagrange equations, the good thing about that is that we have some tools to deal with these kind of equations already. And we have some mathematical and numerical analysis results for this kind of variational formulation of the problem. So we can replace actually the lower level optimization problem with that variational formulation, which is given here. And we have also some approximation results or some numerical results we can use, mainly with finite elements, which is the tool we are using right now with linear finite elements, and we can recover some solution out of it. So the lambda is the parameter that we want to recover in this setting. And a part of that, you have a lot of possibilities concerning the kernel. So you may want to use one or the other, and you have a family of kernels you can use in this setting. And with the different kernels you have, this is called the Yaroslavsky kernel, and the modified non-local means are two examples of the kernels you may want to use in that case. And mainly the aim of the kernel is to explore the similarities of the image in a neighborhood of X. So what you want to learn is actually the pattern intensities, right? So it depends on how you do that, if you take an integral form of the intensities around, or you just take the point-wise values of the function, then you may end up with a different kind of reconstruction in that context. So this is an example of the images processed with different non-local regularizers. And I guess it's difficult to see from the distance, but you have different outcomes, different parameters, and you may have some result which is looking good in a first view, but then you realize the details are missing in that image. But you may want to recover some more details, which are given, for instance, here or here, but you have to tune the parameters. You have to know in advance what to do, right? So that's exactly what we are aiming to, and these are just the first steps towards that task. So our bilevel optimization problem is looking the same way as before. We have the minimization problem in the lower level. We replace the optimization problem, at least for this type of non-local variational term. We replace with the optimality condition, and what we are aiming is to obtain a better reconstruction or an optimal reconstruction of the image. Now there are some previous works concerning that we can take, we can learn from, we can extend, and that's a good news. We don't have to start from the scratch. And what we are trying to do actually in this context is to characterize the optimal solutions, the optimal values of the parameters, but also trying to extend to optimal kernels, for instance, and this by means of a rigorously derived optimality condition. We have to consider a proper discretization scheme, some derivative-based optimization algorithms, and we want also to compare the performance of the different non-local regularizers that are around, right? And also the spatially dependent case, which is something that we are interested in. And finally, some conclusions and outlook of this talk. So first of all, and the main task that we have is to use this learning strategy, this bilevel learning strategy, to analyze, to proper characterize the optimal solutions and the optimal parameters you have to use in some image processing task. And that's something we want to do in the continuum, being able to use PDEs or use variational inequalities for the results. We are able to develop efficient numerics for different type of noise models, and what we hope actually is to be able to cope with non-local models and obtain some results concerning the optimality in that case. And I guess that's everything. So thank you very much for your attention.